And we're going to go back to this triangle section, and we said this one's a little sneaky because there's a couple different types of triangles. So obviously the area formula we'll start with. Area equals 1/2 base times height. So the two things you'll clearly need are a base and a height. Now, here's the tricky part. They didn't leave us room to write this. All right, there are two types of triangles that you'll have to know the difference between. Bless you. The first one is an isosceles. And that's going to get split up into two categories. So first of all, what does isosceles mean? Two of the same side, right? Now, it's going to depend upon the way they describe this triangle. They're either going to say, so I'm going to put a 1 here, leg on the base. Now, to me, the triangle is really important to draw out, and it's less memorizing if I draw them out. So, obviously, when you picture an isosceles, you're picturing two equal sides. We want the leg to be on the bottom part. So it's going to look like this. So please draw that for yourself. Okay, it's a right triangle, and the legs are the congruent sides. Okay. Now, let's just make a note. This is the base. What do I notice about the base and the height when I draw it this specific way? They are what to each other? Equal. So if it's an isosceles triangle with the leg on the base, the key is that the base equals the height. That is key. And again, just by drawing it out, it makes it semi-obvious. Okay, now here's the trickier one of the two. The hypotenuse is on the base. Hypotenuse is on the base. Okay, so I want you to do the same thing. We're going to draw it for ourselves. Every time it's a triangle, draw the triangle. But this time, I need the hypotenuse to be on the bottom, the base bottom. Okay. Right, and again, it's a right isosceles, so I'm going to put my right in, and I'm going to mark my congruent sides. Okay, so I have to think about what the relationship is to the base and the height. So I'm going to go ahead and draw a height, and I'm going to drop a perpendicular line down the middle. And I want you to think about what just happened when we dropped that perpendicular line down. This was a 45, 45, 90. I can put the 45 in there lightly. So what did that do to this triangle? What did it just make this triangle now? What type of triangle do I have in just this corner? Fran? Isosceles again, because this was a 90 and we cut it in half. So that makes this a 45. So what does that tell me? I'm going to mark this one about this height and just this piece of the base. This and this are equal to each other. So now think about this. How does that compare to the entire base? The height then is how much of the entire base? Half, and that's the key. In this case, the height is half of the base. Okay, so you can always talk yourself through it. So I'm going to highlight the important part. If the leg is on the base, you have to understand that the base and height are equal. If the hypotenuse is on the base, then the height is half the base. Okay. Now there's one more triangle they're going to ask about, and I really apologize for the room on here. I'm going to put the third one up here, and this is the equilateral. Okay, the equilateral triangle. Okay, obviously equilateral means all the sides are equal, all the angles are equal. So again, I'm going to draw that equilateral triangle for myself. If they're all equal, what does that make each angle? Dan, what does that make each angle? 60. Okay, so equilateral triangle, they're all 60. And again, our question is, how does that base compare to its height? How does the base compare to its height? Now again, you could drop a nice perpendicular line down, and then you'd get a 30, 60, 90. I'm going to do all the math. I don't know if you necessarily have to write it down, but I could put all the math up here. Let's say we assume all these sides are 1, right? If I took this and cut it in half, it now makes this distance how much? Half. And I can do Pythagorean theorem to get this missing side. So 1 squared minus 1/2 squared is going to be the square root of 3 over 2. So what you need to know in this triangle is that the height equals the square root of 3 over 2 times the base. One way I kind of remind myself of that is I think of this 60-degree angle, and I kind of think of like it's the ratio of the sine, opposite over hypotenuse, is root 3 over 2. It's kind of how I keep it in my head. But this is the ratio we need to know for an equilateral triangle. Okay. So by far, I think, these two are easy, especially if you draw them, you can see them. And then just kind of keep in your head, for an equilateral, we need root 3 over 2 times the base. All right, so like I said, I don't know what happened. I completely missed the triangle questions in here. So let me pass this out. And we'll tackle maybe just a couple together. Okay, so I just want to stress again, all volume is the integral of area. Just keep saying that to yourself. Volume is just the integral of area. So whatever area formula you know, you can make it into a 3D version and find its volume just by integrating it. Okay. I'm going to write this out one more time just so it's staring at us. I'm going to skip down to here to this equilateral triangle. Okay, so I'm just going to draw myself a quick little picture. Equilateral triangle. I want to remind myself that the height is root 3 over 2 times the base. Isosceles, right, there's two cases. So I'm going to say case 1. Bless you. We're going to have the leg on the base. Case 1, leg on the base. And again, I would just draw it. Draw the leg on the base, the bottom. Label your sides that are equal, and then the ratio should be obvious. This base is the exact same as this height, so that's what I have to remember. The base equals the height. Case 2, we're going to have the hypotenuse on the base. And again, I'm just going to draw it so I remember it. Okay, hypotenuse is on the base. That means these sides are equal. And I really want to compare the base to the height. Okay, the height is half the base. And again, you can go through and do the math if you want. That makes that a 45, 45, 45. That makes these two equal, which means that is half of this. Okay. And then since semicircle is staring at us, I'm just going to draw that semicircle one more time. And just a reminder, if this is the base, this is actually the what of the circle, the diameter. Okay, and then don't forget, you need to find the radius by cutting that in half. That's what we talked about yesterday. All right. So we'll set a few of these up. Again, you kind of just have to get your hands dirty and practice them. Be super careful who we're perpendicular to. So question 1, they're going to go semicircle. So I'm just going to highlight who we're doing. Semicircle, perpendicular to the x-axis. So go ahead and put your slice in there. Perpendicular to the x-axis. Okay. You want to ask yourself, is one slice enough? Does that one slice always have the same top and same bottom? I think so as you slide it. All right, so we're going to set up our cross section for a circle. So area equals 1/2 pi r squared. So again, we're picturing this is our base. This is the slice, and this is our base. So this upper minus lower represents that diameter. My upper is on, this is the line y equals 2. And my lower is on the cubed root of x. Okay, upper minus lower. Therefore, if I want the radius, I just need to take that function and cut it in half. So I'm just going to put it over 2. I'm going to jump to writing just the volume out. You can write the area first if you want, but I think you could probably put it all together here. So I'm going to say volume equals the integral. Now I need the area. So I need 1/2 pi, and then I need whatever I wrote for r and square it. So that's 2 minus the cubed root of x over 2 squared dx. 1/2 pi, whatever I wrote for radius squared. Okay, then we got to talk bounds. So we're going to take that slice, it's vertical, so it can move left and right. So I think the left is obvious. How far to the left can it go? 0. And how far to the right? Now, if you can't tell, you're just looking to see where these two functions are equal, where 2 is equal to the cubed root of x. And to get rid of that cubed root, I would just cube both sides, bless you. So I think we get x equals 8. So I would say from 0 to 8. We'll set up the first two, and then we'll play with the calculator maybe on the next one. We'll just kind of go set up here. All right, let's try number 2. Off to the right here. So equilateral triangle, okay, whose cross sections are annoying and perpendicular to the y-axis. Okay, this is the real annoying one. So now draw your slice horizontal. You're now perpendicular to the y-axis. And the reason this one's annoying is everything has to change. All the variables, all the bounds, everything changes. So the first thing I want to say, is one slice enough? Is this always on the right and this always on the left? I think so. I think that works. Okay, so now I want to picture, first of all, the equilateral triangle. So think back to what we said the ratio is for the equilateral triangle. So first I'm going to start with 1/2 base times height. Bless you. And in the equilateral, bless you, we said the height is how much of the base? Root 3/2 times the base. Okay. So I'm picturing this as an equilateral triangle coming out at me. The base is my right minus my left. So I need the right minus the left. Now I can't just write this down because it has to be in terms of y. So I have to take that function, y equals the cubed root of x, and I have to solve for x. All I'm going to do is cube both sides, and x equals y cubed. So my right is on y cubed, and my left is actually just on 0. So I could really just call it y cubed. Okay, so there's my base. My height is the cubed root over 2. I'm sorry, cubed root of, I can't speak today. Square root of 3/2 times the base. So square root of 3/2 times my base of y cubed. So again, it's just what we said the ratio is, cubed root of 2 times the base. And now I'm going to integrate. So my volume is the integral of the area formula, which we said is 1/2. Whatever I wrote for base, so y cubed, times what I wrote for height, cubed root of 2 times y cubed. So there's my 1/2. There's my base. There's my height. And I'm just going to slap a d y on the end. Okay, now I have to get the bound. So I'm saying, where does this slice move? It's not moving left or right. It's moving up and down. How low does it go? 0. And how high does it go? 2. 0 to 2. All right, so the next one, I'll give you a minute to set up, and then we're going to solve in the calculator. All right, so read it to yourself. We'll put a few minutes on the clock, and then grab your calculator to evaluate. I'll just talk through my setup again. So I just start with the area formula. I drew a picture so I can see the ratio. When I drew it, it looks like the base and the height are the same, so that's what I'm saying. This slice is the base of the triangle coming out. So my base is upper minus lower, so square root of x minus 1 minus 0. The base equals the height according to the ratio, so that's the exact same thing. And then I just throw it in the volume formula. So it's 1/2 whatever I wrote for base times whatever I wrote for height. Since it's the same thing, I could easily just call that squared, or you could simply write it twice, dx. Okay, nothing wrong with writing it twice, 1/2 base times height. My bounds look like they go, I can move this slice from 1 to 3. How'd that setup look? Okay, and then again, I'm just going to throw that in my calculator, math 9, 1 to 3. You can pull the 1/2 out front if you want. And I have that function in y1, which I missed the square root of. y1 squared. Does that look like your answer? I'm getting a no. I'm getting a not so much. Do I have that in there? X minus 1. Brian, did you get something different? You did too. 1/2. Well, What the heck? You got 1 also? All right, all right. X minus 1. Does my formula look like yours?
I remember in the y equals, I just put all the in like radical x times 1 times radical x times 1.
Yeah.
I don't think you should have the square root on it, like when you're calculating it, like in the integral. If you have like another square root.
Oh, because I already typed it in. Oh, Jiminy Crickets. This Monday's getting to me. You are 100% right, Abby. How about 1? Thank you. All right, number 4. So this time they're going semicircle, okay, and the annoying cross-section perpendicular to the y-axis. Cross-section perpendicular to the y-axis. All right, so I'm going to slide it this way. I'm going to start with my semicircle, 1/2 pi r squared. So same thing, take a minute. All right, I'll just compare setups again. So I've got my horizontal slice this time, so I'm picturing this semicircle coming out here. This distance, my right minus my left, represents the diameter. So I'm going to say my diameter, the right side is 3. And then when I solved this equation for x, I've got y squared plus 1. So I'm going 3 minus the quantity y squared plus 1. The radius then is going to take that amount and cut it in half. So I'm going to just call it over 2, or times 1/2, doesn't matter. And then again, to integrate, or to find the area, I'm just going to put my whole area formula in there, 1/2 pi. And then whatever I wrote for radius, and square that with a dy. Have I lost anybody on that? All right, so now I'm going to talk bounds. This slice is moving up and down. I think the lowest is obvious. That height is 0. The upper height isn't obvious. I know the x value is 3, but I need the y value here. I need the height here. So I actually can't just set those two equal to each other, right? Because this is an x equals 3. I'm literally just going to plug in 3. So y equals the square root of 3 minus 1, or y equals the square root of 2 should be that upper height. When I plug in 3 into this equation, I get the square root of 2 for the y value. And then I'm going to carefully type this in. Now, I just wanted to really stress what we talked yesterday is that we can't use y on the calculator, so we still call it an x. I just put the x squared plus 1 into my y2, just so I don't have to retype it and make any extra errors that I'm apparently already making this morning. But again, I'm only using x on the calculator. So let's see if I can type this in correctly. I'm going 0 to root 2. Got my 1, not there, can't type it in correctly apparently. Square root of 2. Got my 1/2 pi, which again you could pull out front. And then I'm going to go 3 minus, this is in my y2, over 2 squared. I think I got that in there. How does that look? 1.185. 1/2 pi, that minus that squared over dy. All right, let's see. I want to try just maybe one more on here that we haven't done. We did equilateral, semicircle. Let's try just this number 6 here. Okay, so based off this function, we want an isosceles right triangle. So there's our key, whose hypotenuse is on the base and then perpendicular to the y-axis. Okay, isosceles right, hypotenuse on the base, perpendicular to the y. So again, I'm going to draw out that hypotenuse on the base for myself. And then hopefully when I drop that height down, I'm reminding myself that I'm cutting it in half, so the height is half of the base. Okay, 2 of those compared to 1 of those. The ratio is 1 to 2. The height is half the base. All right, so I'm going to draw my horizontal slice. I think this is always on the right and this is always on the left, so 1 slice is good. Again, we'll put a few minutes on the clock and talk yourself through that one. Everyone's in there. So again, I'll just walk through what I had. I drew my triangle. I said it looks like that height is half the base. That's my ratio. I need my right minus my left. So I had y equals 2 ln of x. I know I need to use an e to get rid of an ln, but somebody's in the way. So I first have to divide out the 2. So y over 2 equals the ln of x. Then I can raise both sides to the e. So I'm going to say x equals e to the y over 2. Okay, so my right is e to the y over 2 minus my left, which is sitting on this line, which happens to be 1. So again, I'm just describing this base. So I've got this triangle that looks like this. Base is right minus left. The height is half of what I wrote for my base, e to the y over 2 minus 1. So then the area is just 1/2 whatever I wrote for base times whatever I wrote for height. So because those are the same, I could say it's that quantity squared, or I could literally write them twice. So that's my 1/2 from the triangle times the 1/2 from this. And I have e to the y over 2 minus 1 squared dy. Or again, you could have written it out twice. This first 1/2 is from the area formula. The second 1/2 is from the height. Okay. Talking bounds, this thing is sliding up and down, so it looks like it goes down to 0 and it goes up till 2. So I'm just going to say from 0 to 2. Anybody lost on that setup? That needs a further explanation? Go ahead, Ry. Any?
You mean like when it says like perpendicular to the y-axis, where it's kind of, it seems kind of like upright?
So the slice here itself, the base is perpendicular to the y-axis. The triangle is coming out of the paper at us, that 3-dimensional part that's coming out at us. Okay, so remember, these are all, you know, looking at that slide we did before, that here, everything we're doing is coming up out of the paper at you, making it a 3-dimensional. This base here is what we're describing. The right minus left, or upper minus lower. All right, let me give you this just so it has answers. I don't think the rest will have any answers to match. This will be our homework sheet here. a good 8 minutes or so. Go ahead and get the first two underway at least, and then we can compare if you're not getting anything. Yeah.
When you put this in, sorry, do you use the function that we communicate with x equals, or do you plug in the main version of it?
No, you're using this.
Okay.
Yes.